Vibration analysis. Time and frequency analysis technique Part 2. At this time, our agenda will talk about number 1 is natural frequencies, number 2 is multiple frequencies, linear systems. It will focus on high frequency writing a low frequency. Number 3 is multiple frequencies, nonlinear systems. It will focus on amplitude modulation. Number 4 is sum and difference frequencies. Number 5 is pulses. And number 6 is frequency modulation. Vibration analysis. Time and frequency analysis technique. Natural frequencies. A special case occurs when natural frequencies are excited. A discrete frequency is not present in such cases because the natural or excited frequency is a band of frequencies. In this situation, a band of spectral lines occurs. The bandwidth is determined by damping, and the difference frequency between the spectral lines is the source of excitation. A high degree of measurement accuracy is required to determine if a given frequency is an excited or neutral frequency or a generated frequency or events times speed. Amplitude modulation can occur between two generated frequencies, or an excited frequency can be modulated by the source of excitation, that is, a generated frequency. When a generated frequency equals an excited frequency, other tests and measurements must be employed to identify the excited and generated frequencies. These techniques will be discussed in following section. Vibration analysis. Time and frequency analysis technique. Multiple frequencies linear systems. High frequency writing a low frequency. When two independent frequencies are present in a linear system, they cannot add together an amplitude or frequency. When this occurs, the two frequencies mix, and the high frequency will ride the low frequency, as in Figure 26. At first glance, amplitude modulation appears to be present. However, close inspection indicates that the two envelopes enclosing the peaks of the time signal are in phase. This means when the positive peaks of the signal move upward, the negative peaks of the signal move upward. The time period for one cycle of the envelopes is 50 milliseconds or 20 Hz, which is the low frequency as shown in this equation. Frequency equal to 1 divided by time variable, equal to 1 divided by 50 milliseconds equal to 20 Hz. 5 cycles of the signal are contained in each cycle of the envelopes, and the time period for each cycle of the signal is 10 milliseconds or 100 Hz, which is the high frequency, as shown in this equation. Frequency equal to 1 divided by time variable, equal to 1 divided by 10 milliseconds equal to 100 Hz. The peak-to-peak amplitude of each cycle is 2 times the zero-to-peak amplitude of the 100 Hz frequency. 2 multiplied by 4.0 engineering units equal to 8.0 engineering units. The peak-to-peak amplitude of each envelope is 2 times the zero-to-peak amplitude of the 20 Hz frequency. 2 multiplied by 1.0 engineering units equal to 2.0 engineering units. The zero-to-peak value of the highest envelope peak is the amplitude of the 100 Hz frequency plus the amplitude of the 20 Hz frequency. For engineering units, add by 1 engineering units equal to 5 engineering units. The lowest point of the envelope is the amplitude of the 100 Hz frequency minus the amplitude of the 20 Hz frequency. 4.0 engineering units minus by 1.0 engineering units equal to 3.0 engineering units. Since harmonics are not present and the high frequency is writing the low frequency, there is not a cause and effect relationship. The two signals are generated independently. It is important to note that a high frequency, which is an exact multiple of a low frequency, will cause the amplitude of the high frequency peaks to be the same in each period of the low frequency. A high frequency that is not a multiple will cause the amplitude of the high frequency peaks to vary during each period of the low frequency. Vibration analysis. Time and frequency analysis technique. Multiple frequencies nonlinear systems. Amplitude modulation. 2 or more independent frequencies can be mixed together if a machine has some form of nonlinearity or other problem. There are many forms and degrees of frequency mixing. Examples of amplitude modulation, sum and difference frequencies, pulses, and frequency modulation are discussed in the following sections. Amplitude modulation occurs when two frequencies are added together algebraically. Frequencies will not add in a machine that behaves in a linear manner. Therefore, a problem must exist before amplitude modulation can occur. There are several forms of amplitude modulation. One form is a beat. A beat occurs when the amplitudes of two frequencies are added together. Assume there are two frequencies BF 29.6 Hz and 25.6 Hz, as in figure 27. There are similarities between a high frequency writing a low frequency and amplitude modulation. The maximum 0 to peak envelope amplitude is equal to the amplitude sum of frequency 1 add by frequency 2, as shown in this equation. 0.6 engineering units add by 0.15 engineering units, equal to 0.75 engineering units, equal to 0 to peak envelope maximum. The amplitude difference of frequency 1 minus by frequency 2 is the minimum 0 to peak envelope amplitude, as shown in this equation. 0.6 engineering units minus by 0.15 engineering units, equal to 0.45 engineering units, equal to 0 to peak envelope minimum. The time period for each cycle in the time signal is 33.9 milliseconds, which is the 29.6 Hz frequency, as shown in this equation. Time period equal to 1 divided by 29.6 Hz, equal to 0.0339 seconds. The envelope frequency, however, is not the 25.6 Hz frequency, as it was for a high frequency writing a low frequency. For amplitude modulation, the envelope frequency is the difference between the two frequencies, frequency 1 minus by frequency 2, equal to 29.6 Hz minus by 25.6 Hz, equal to 4 Hz. Figure 27 contains a complete cycle of the difference frequency of 4.0 Hz. The envelope occurs at a time period of 250 milliseconds, as shown in the equation. Time period equal to 1 divided by 4.0 Hz, equal to 0.25 seconds, equal to 250 milliseconds. Amplitude modulation is the result of a cause and effect situation, and the amount of modulation can be expressed as a percentage. The frequency spectrum identifies the percent modulation as the amplitude of the lower frequency divided by the amplitude of the higher frequency, as shown in the equation. 0.15 engineering units divided by 0.60 engineering units, equal to 0.25, or 25%. The percent modulation in the time signal is expressed as the maximum envelope amplitude or mx, where mx equal to frequency 1 add by frequency 2 equal to 0.6 add by 0.15 equal to 0.75, minus the minimum envelope amplitude or mi, where mi equal to frequency 1 minus by frequency 2 equal to 0.6 minus by 0.15 equal to 0.45. Divided by the maximum envelope amplitude or mx, plus the minimum envelope amplitude or mi, as shown on this equation. Mx minus by mi divided by mx added by mi, equal to 0.75 minus by 0.45 divided by 0.75 added by 0.45, equal to 0.3 divided by 1.2, equal to 0.25, equal to 25%. Vibration analysis. Time and frequency analysis technique. Multiple frequencies. Comparison between linear and nonlinear systems. Some comparisons between a high frequency writing a low frequency and amplitude modulation are: number 1 is, the envelopes at the top and bottom of the signal are in phase for a high frequency writing a low frequency. The envelopes are out of phase for amplitude modulation. Number 2 is, for a high frequency writing a low frequency, the 0 to peak amplitude of the envelope is equal to the amplitude of the low frequency. For amplitude modulation, the 0 to peak amplitude of the envelope is also equal to the amplitude of the low frequency. The 0 to peak amplitude of the highest peak is equal to f1 added by f2, and the 0 to peak amplitude of the lowest peak is equal to f1 minus by f2 for both a high frequency writing a low frequency and amplitude modulation. Number 3 is, in rotating machinery, a high frequency writing a low frequency, there is no cause and effect relationship. There are two independent frequencies and two independent problems. In amplitude modulation, there is a cause and effect relationship because there are two or more frequencies and only one problem. Number 4 is, when a high frequency rides a low frequency, the reciprocal of the envelope time period is equal to the low frequency. In amplitude modulation, the reciprocal of the envelope time period equals the difference between frequency 1 and frequency 2, or f1 minus by f2. When two frequencies beat together, such as in figure 27, there is a cause and effect relationship. Therefore, two frequencies are present, but only one problem exists. The 29.6 Hz frequency is the carrier frequency and is the effect of the problem, that's the motor is loose. The 25.6 Hz is the modulation frequency or modulator and is the speed of the fan driven by the motor. The only way the fan can shake the motor, in this case, is when the motor is loose. Looseness in the motor allows the motor to shake, and the two frequencies to beat. Amplitude modulation also occurs when two frequencies are not exact multiples. Figure 28 contains two frequencies with second harmonics. The two frequencies are almost the same, but not exact. The signal seems to be constant. However, figure 29 contains the same signal with a longer time period, and it is clear the signal is changing. Figure 30 contains a full beat and amplitude modulation is evident. The difference between frequency 1 and frequency 2 is 0.2 Hz. Therefore, one beat takes 5 seconds to complete. As the frequencies get closer together, the time to complete one beat becomes longer. Therefore, it is extremely important to determine whether the frequency is a harmonic or is just close to the harmonic frequency. The beat in figure 30 is a common signal from a 3600 RPM motor that has an electrical problem. The motor speed is 60 Hz minus the slip frequency, when under a load. Line frequency is 60 Hz. In this case, the motor speed and line frequency must be examined with enough resolution to identify the true problem. Vibration analysis. Time and frequency analysis technique. Sum and difference frequencies. Another type of amplitude modulation occurs when one component is eccentric. A frequency of 100 Hz with a sum and difference frequency of 4 Hz is presented for analysis. The 100 Hz carrier frequency is contained in figure 31. One example of sum and difference frequencies is gear eccentricity. When one gear is eccentric or out of round, the amplitude of gear mesh frequency increases when the high place or places go into mesh. If the gear has only one high place, the signal amplitude will be higher once each revolution. In either case, amplitude modulation is caused by the eccentric gear. The associated spectra contain a spectral line at gear mesh frequency with sidebands of gear speed. If the gear has more than one high place, then the difference frequency between the gear mesh frequency and the sidebands is equal to the number of high places times the speed of the problem gear. If two high places are present, the difference frequency is 2 times gear speed. 3 high places would generate a difference frequency of 3 times gear speed, 4 high places would generate 4 times gear speed, etc. Assume the 100 Hz frequency is gear mesh frequency and gear speed is 1 Hz, if the gear has 100 teeth. If the gear has 4 high places or eccentricities, 4 times gear speed is 4 Hz. Figure 32 shows the 100 Hz frequency with the sum frequency of 104 Hz, equal to 100 Hz added by 4 Hz, equal to 104 Hz. This signal has amplitude modulation. The carrier frequency is the gear mesh frequency of 100 Hz. The modulator or cause of the problem is the 4 Hz frequency of 4 times gear speed. The envelope frequency is 4 Hz and is noted in figure 32 as 250 milliseconds. 100 cycles of gear mesh frequency occur each revolution of the gear. The modulation occurs at 25 cycles of gear mesh frequency or 4 times per revolution of the gear. The modulation is 10%. Figure 33 contains the time period for one revolution of the gear. For modulations can be observed as below equation, t equal to 1 divided by 1 Hz, equal to 1 second, equal to 1000 millisecond. If the eccentric gear has not caused looseness, sidebands will occur at gear mesh frequency plus gear speed or multiples of gear speed. In other words, the sidebands will be on the high side of gear mesh frequency. The frequencies add, in this case, because the phase relationship between the carrier and the modulator is constant. As stated earlier, the machine is behaving in a linear manner. Figure 34 contains the 4 Hz as a difference frequency of 96.0 Hz calculated by 100 Hz minus by 4 Hz equal to 96.0 Hz. The time signal appears similar to figure 32. When a gear or geared shaft system is loose, the looseness causes the modulator to subtract from the carrier because the two frequencies are out of phase. When the two frequencies are in phase, they add. Looseness causes an out-of-phase condition. Eccentricity is an in-phase condition. Figure 35 contains both the sum and difference frequencies. The beat is now more pronounced and the modulation is 20%, calculated by 0.6 minus by 0.4, divided by 0.6 added by 0.4, equal to 0.2 divided by 1.0, equal to 20%. This occurs when both the 96.0 Hz and 104.0 Hz sidebands are in phase. Figure 36 contains both the sum and difference frequencies, but the 96.0 Hz difference frequency is 180 degrees out of phase. In this case, the modulation is 0%. Modulation on the high side, or a sum frequency, indicates a linear problem. Low side modulation, or a difference frequency, indicates a nonlinear problem. Therefore, because of the nonlinearity, the phase of the difference frequency will be changing. However, the sum frequency will maintain its phase relationship. If gear eccentricity has caused looseness, nonlinearity, associated with the problem gear, sidebands can occur on both sides of gear mesh frequency. If looseness is the more severe problem, the amplitudes of the sidebands will be higher on the low side of gear mesh frequency. If eccentricity is the more severe problem, the amplitudes of the sidebands will be higher on the high side of gear mesh frequency. If looseness is the only problem, then the sidebands occur only on the low side of gear mesh frequency. For example, suppose a gear was mounted on a shaft rotating at 29.6 Hz, gear mesh frequency was 1280 Hz, and the bearings were loose in the housing. Gear mesh frequency would be present in one sideband could occur at 1160 Hz calculated by 1280 Hz minus by 4 multiply 29.6 Hz equal to 1160 Hz. 4 times running speed is an indication of slippage, so 4 multiply by 29.6 Hz is generated. The frequencies subtract when looseness is present because the phase relationship between the signals is not constant, which means the machine is acting in a nonlinear manner. This technology is not new. It has been used for years to identify moving targets with radar, and for space object identification to determine the shape as spherical, cylindrical, triangular, bell-shaped, etc. It has also been used to identify the way an object is moving, i.e., amount of spin, tumble, pitch, and yaw. However, these principles had not been used for rotating machinery until the author applied the technology. The principles described for gear mesh frequency apply to other generated frequencies such as blade or vane pass frequencies, bearing frequencies, frequencies from multiple defects, and frequencies from bars or corrugations on press rolls. Vibration analysis. Time and frequency analysis technique. Pulses. A pulse is caused by a hit or an impact. Pulses fall into one of 3 categories: empty pulses, frequency modulation, and amplitude modulation. Figure 37 contains an empty pulse. This occurs when excited or generated frequencies are not present. It is called empty because it contains no generated or excited frequencies. A pulse is identified by a series of spectral lines. The repetition rate of the pulse is equal to the difference frequency between the spectral lines. The empty pulse has a low-level spectral line at shaft speed, and the amplitude increases with each succeeding harmonic. Frequency modulation is a time-varying frequency. This frequency modulation can appear as a series of bursts or beats, as contained in figures 38 and 39. Generated or excited pulses are usually caused by a once-per-revolution impact or excitation. Figure 38 contains a series of spectral lines. The pulse repetition rate is equal to the difference frequency between the spectral lines, or 500 milliseconds. This would be similar to an impact once per revolution. Figure 39 is a representation of a felt problem. The pulse or bad place in the felt is exciting a natural frequency of the loading diaphragm. The pulse repetition rate is 0.5 Hz, or 2 seconds, which is once per revolution of the felt. The signals in these figures contain characteristics of both amplitude and frequency modulation. Again, it is impossible to determine the character of the time signal from the frequency spectra. Vibration analysis. Time and frequency analysis technique. Frequency modulation. Frequency modulation is a time-varying frequency, as opposed to amplitude modulation, which is a time-varying amplitude. The lower frequency is the carrier, and the higher frequency is the modulator. The modulator is normally an excited frequency, and the source of excitation is normally the speed of the rotating unit. Figure 40 is an example of frequency modulation. The low frequency carrier is 10 Hz, the excited high frequency is 50 Hz, and the source of excitation is the 2 Hz difference frequency. The high-frequency bursts occur at 2 Hz intervals. This could occur in a pump when pump speed is 2 Hz, and the impeller has 5 vanes. The 10 Hz carrier frequency is vane pass frequency. The problem or source of excitation is 1 impact per revolution of the impeller. If one vane hit the housing, the 50 Hz frequency could be the natural frequency excited by the impact. Frequency modulation can be a series of high-frequency bursts similar to a pulse, or the high frequency can occur periodically with a low frequency. Since the frequency response of an accelerometer is best at high frequencies, such problems may be best measured in acceleration. Frequency modulation occurs most often in impacts, such as defects on the inner race of cylindrical roller bearings, or when 2 shafts are rotating very close to each other. Frequency modulation can occur in screw compressors, vacuum pumps, and blowers when one shaft is bent enough to permit an impact once each revolution. One last comparison should be noted to clarify the differences between a high frequency riding a low frequency, amplitude modulation, and frequency modulation. Number 1 is high frequency riding a low frequency. No looseness is present. High and low frequencies may be exact multiples of each other. No mixing of signals occurs. Changes in the phase have little or no effect. Number 2 is amplitude modulation. High frequency is the carrier, low frequency is the modulator. Signals go into and out of phase, and number 3 is frequency modulation. Low frequency is the carrier, high frequency is the modulator. Vibration analysis. Time and frequency analysis technique. Conclusion. All machines obey the basic laws of physics. Therefore, vibration problems are repeatable and can be identified. Both the time signal and frequency spectra must be analyzed to accurately identify problems. This was proven both empirically and theoretically. The basics of time domain analysis were discussed and used to explain the frequency spectrum. Single frequencies and single frequencies with harmonics were explained to identify the effects of amplitude changes in phase relationships. Using these basic principles, multiple frequencies were introduced to identify linear and nonlinear problems for more complex analysis. Multiple frequencies include high frequencies riding low frequencies, amplitude modulation, beats, pulses, and frequency modulation. It was also noted that if there is a cause-and-effect relationship in the signal, a problem exists in the equipment. The fundamental concepts in this chapter are the foundation for understanding and explaining the preceding chapters. Using these fundamental concepts, all time and frequency relationships can be understood. However, with the many combinations of phase shifts and amplitude changes, each case needs to be analyzed to identify all the information contained in the vibration signal. Analysis can be complex and time-consuming, but the use of Signal Analysis Program (SAP) simplifies the analysis. The result is a complete and more accurate diagnosis of machinery vibration problems. Thank you.